Parallel with the numerical description of a numerical variables, we now study the relationship between two random variables in this part of the lecture. The joint probability distribution between two random variables, say x and y, is denoted as P of x and y. It is essentially a table or formula that lists the joint probabilities for all pairs of values of x and y. The joint probabilities between two random variables is also called the bivariate probability distribution. By definition, the joint probabilities between these two random variables must be a number between 0 and 1. And the summation of all the joint probabilities over all the pairs of values of x and y must be equal to 1. Now, let's take a look at an example. Let's say there are two real estate agents, Xavier and Yvette, serving the same residential area. Let the random variables x and y denote the number of houses sold in a month by Xavier and Yvette respectively. Both of these random variables can take values 0, 1, and 2. The table on the slide shows the bivariate probability distribution between these two random variables. Let's take this number, 0.42, as an example. It means that the joint probability that Xavier sells one house and Yvette makes no sale is 42% of the chance. All the other numbers can be interpreted similarly. Then the marginal probability assigns the probability distribution for only one of the two random variables. It is computed by summing up the joint probabilities across the row or down a column in the previous table. We can then calculate the corresponding mean, variance, and standard deviation for each individual random variable using the marginal distribution. Now, let's see how to compute the marginal probability distribution for x and y respectively in the previous example. As we have learned before, covariance and correlation are two important numerical measures of a linear relationship between two numerical variables. We can generalize these concepts to random variables as well. The covariance between two random variables x and y is computed as the weighted average of the product of the deviations from the means for both x and y, where the weights are the joint probabilities between x and y. It can be simplified to first compute the weighted average of the product of x and y, and then minus the product of their individual means. The correlation coefficient is defined in the same way as before, namely the covariance between x and y divided by the products of their individual standard deviations. Now, let's compute the covariance and correlation in the previous example. In general, given two random variables together with their means, variances, and covariance, we have the following formula to compute the expected value and the variance for a linear combination of these two random variables. The expected value of the linear combination of two random variables is equal to the linear combination of their expected values. That is, again, the linear transformation and the expectation operation are interchangeable. The variance of the linear combination of the two random variables, ax plus by, where a and b are two constants, is equal to a squared times the variance of x plus b squared times the variance of y plus 2 times a times B times the covariance between X and Y. If you can still recall your high school algebra, this formula over here is actually reminiscent of the square of the sum formula. Please do not forget about the 2 in front of the covariance term. These two formulas are referred to as the law of expectation and the law of variance for weighted sum of 2 random variables. If X and Y are independent, then the covariance between X and Y must equal to 0. Then the above law of variance reduced to simply A squared times the variance of X plus B squared times the variance of Y. Then the covariance correction term dropped out of the equation. If you are given the coefficient of a correlation between these 2 random variables, say rho, you can actually substitute the covariance between these 2 random variables by rho times the product of their individual standard deviations. More generally, for arbitrary number of random variables, we have the general laws of expectation and variance for their linear combinations. Let's suppose we have k random variables, x1, x2, up to xk. Then for any given constant weights, w1, w2, up to wk, the expected value of the weighted sum of these k random variables is equal to the weighted sum of their expected values. That is, the expectation operation and the linear transformation are interchangeable. The variance of the weighted sum of these k random variables can be calculated as follows. First, we calculate the sum of the product of the square of the weights with the variance of that random variable. And then we need to add a correction term. The correction term is equal to 2 times the sum of the product of their weights multiply the covariance between all the distinctive pairs of the random variables. Let's look at some examples to get a real feeling about these formulas.